Dear students, now we will do the second application of Ampere circuital law, that is a solenoid. A solenoid consists of number of insulated turns over a rod. The speciality of a solenoid is its length is very large as compared to its diameter. In 10th class, you have studied about solenoid. In Hindi, solenoid is named as parinalika. Now, the solenoid we have taken here is infinitely very long, and we know that the magnetic field inside the solenoid is always constant and no magnetic field exists outside the solenoid. Now we have to calculate magnetic field intensity at any point on the axis of a solenoid. Now we consider this rectangular loop inside the solenoid. This is a solenoid, and for finding out the magnetic field inside it, we considered a rectangular loop P, Q, R, S and again P. This closed rectangular loop we have considered. Now using Ampere circuital law, we write it as B dot dl integral of P, Q, R, S, P, that is the complete closed rectangle. Now we will find the line integrals of the four sides of the rectangle. Firstly, we will write for the first side, that is PQ, B dot dl PQ. After then we will write for this side, that is QR, QR B dot dl. After then for this side RS, integral RS B dot dl. Then again for this side, that is SP B dot dl. Now we can see that initially for the first arm, when we write integral PQ B dot dl, when we remove dot then we get cos. Here we write cos 0 because B and dl, they are pointing in the same direction. The direction of magnetic field B is this, and when we are considering this side PQ, the direction of PQ is again this. B and dl both are pointing in the same direction, it means angle between them is 0 degree. When two quantities point in different directions, then there is some angle. But when both the physical quantities are pointing in the same direction, then angle between them is 0 degree. So we write B dl cos 0. Now in the second, we can see that in second we have B dot dl cos 90. The angle between B and dl is 90 here. The magnetic field B is pointing in this direction and we are taking this side QR. QR is pointing in this direction. That's why the angle becomes 90 degree. So we write cos 90 here. Now RS B dl. RS is this side. This side lies outside the solenoid, so the magnetic field B becomes 0 here. This term vanishes as no magnetic field exists in the current arm RS. Now we will talk about SP, the side SP. In the side SP, this is the side SP. Again magnetic field is pointing in this direction and SP is pointing in this direction. So angle becomes 90 degree. So we write cos 90 here. Now cos 90 becomes 0 and we get only the first vector, that is B dot dl, B dl cos 0. Cos 0 is 1. So we get integral PQ B dl. At last we get B dot dl for the complete rectangular coil as integral PQB dot dl. Now the integration of dl is complete length, that is denoted by capital L. In the rectangle, the length PQ is given by complete L. So we write complete L in this expression. Now, the total current enclosed by the complete loop can be written as Ni. There are n number of turns within the length L of PQ. So the current enclosed by the loop can be written as Ni. We can write BL is equal to mu naught Ni. By using Ampere circuital law, we know that the magnetic field is directly proportional to current. B dot dl is equal to mu naught I. We write here mu naught Ni because the total current enclosed by the loop is Ni. Now we can write B is equal to mu naught N upon Li. N upon L is number of turns per unit length. We can denote it by small n, and as the final result we can write B is equal to mu naught Ni, where n is number of turns per unit length. This is an important expression for solenoid. Inside the solenoid, the magnetic field is always constant and it is equal to B is equal to mu naught Ni. And outside the solenoid, the magnetic field vanishes to 0. When we talk about the ends of the solenoid, at ends of the solenoid, the magnetic field, the value of the magnetic field reduces to half. It means when we talk about the ends, then we can write capital B is equal to mu naught Ni divided by 2. This is for ends of the solenoid. Otherwise, inside the solenoid, the magnetic field is B is equal to mu naught Ni. This is the final result. It will be used in numericals. Thank you.